Did you know there's a lighting technology that doesn't rely on bulbs or filaments, yet produces light brighter and more natural than most LEDs? The best part? It consumes even less energy than conventional lighting solutions. This groundbreaking innovation, known as Light Emitting Plasma, LEP, operates using microwaves, sounding more like science fiction than reality. Despite its futuristic mechanism, LEP is very much real and has been employed in high-end applications like film projectors, scientific labs, and stadium lighting. Yet, it remains one of the most underrated and fascinating lighting technologies today. So why has such an advanced and efficient lighting solution faded into obscurity?
The answer lies in a mix of high costs, technical complexities, and the rapid rise of LED dominance. LEP technology generates light through plasma excitation, setting it apart from traditional lighting methods. Unlike incandescent bulbs or fluorescent tubes, LEP lamps contain no filaments or electrodes that wear out over time.
Instead, they use a small quartz capsule filled with specialized gases like argon, krypton, and metal halides. When activated, a 2.5 GHz radio frequency field, similar to a microwave's magnetron, excites these gases into a plasma state. The result? A tiny, self-contained star that emits intensely bright and natural light. This plasma-based illumination offers a continuous spectrum, closely mimicking sunlight and providing superior color rendering. One of the most striking features of LEP is its ability to produce high-quality light without physical electrodes. Since there's no direct contact, the system avoids the wear and tear that plagues traditional bulbs. This design grants LEP lamps an impressive lifespan of around 50,000 hours, far exceeding most conventional lighting options. However, the technology isn't without its drawbacks, the biggest being its slow startup time. Unlike LEDs that provide instant light, LEP lamps require a warm-up period, gradually increasing in brightness and color accuracy. Early in the ignition phase, the light appears overly blue with poor color rendering, but it stabilizes into a crisp white glow. Another major hurdle is cost. LEP systems demand specialized radio frequency generators and ballasts, making them expensive to produce and install. Their bulky size further limits their practicality for everyday residential use. Originally developed in the late 1990s, LEP entered the commercial market between 2005 and 2007, right as LEDs began their meteoric rise. Had LEDs not surged in affordability and efficiency, LEP might have dominated modern lighting.
Some cities, like Los Angeles and Kansas, even tested LEP streetlights in pilot programs before ultimately switching to LEDs. Despite its niche status, LEP still finds use in specialized areas like sports arenas, agricultural grow lights, and high-precision scientific environments. Its ability to simulate natural sunlight makes it ideal for indoor farming, where plants thrive under its full-spectrum output. There have even been experimental applications in automotive headlights, though cost and complexity hindered widespread adoption. The story of LEP serves as a fascinating what-if in lighting history, a superior technology overshadowed by market forces. So, would you like to see this forgotten innovation make a comeback? Perhaps future advancements could address its limitations, giving plasma lighting a second chance. Until then, LEP remains a brilliant yet overlooked chapter in the evolution of artificial light. Despite its incredible efficiency and light quality, LEP technology faced an uphill battle against the rapid advancements in LED lighting. The timing of its commercial release couldn't have been worse, arriving just as LEDs were becoming cheaper and more versatile. While LEP offered superior brightness and color accuracy, its high production costs made it impractical for mass-market adoption. The need for complex microwave generators and specialized ballasts drove up prices, putting it out of reach for everyday consumers.
Even industrial and municipal projects, which could afford the initial investment, eventually shifted to LEDs due to their instant-on capability and modular design. Another critical flaw was the warm-up period. LEP lamps took valuable minutes to reach full brightness, a deal-breaker for many applications. Imagine waiting for a streetlight to gradually brighten instead of instantly illuminating a dark road. This delay was a major drawback. In contrast, LEDs provided immediate, flicker-free light, making them the preferred choice for everything from home lighting to traffic signals. The sheer bulkiness of LEP systems also limited their use, as they required significant space for installation compared to compact LED fixtures. Despite these challenges, LEP found a niche in environments where light quality and intensity mattered more than cost or convenience. Film studios, for example, prized its near-perfect color rendering, which helped cameras capture scenes with stunning accuracy. Scientific laboratories also benefited from its pure, steady light, ideal for precision instruments and experiments. Even in agriculture, LEP proved valuable. Its full-spectrum output mimicked sunlight, promoting healthier plant growth in indoor farms.
Some forward-thinking engineers even experimented with LEP as automotive headlights, drawn by its unmatched brightness and range. However, the technology's complexity and regulatory hurdles around microwave emissions stalled these ambitious projects.
Interestingly, a few cities worldwide gave LEP street lighting a chance in the late 2000s, running pilot programs to test its viability. Los Angeles, for instance, installed LEP lamps in select areas between 2008 and 2011, evaluating their performance against traditional sodium vapor lights. The results were mixed. While the light quality was exceptional, maintenance costs and energy efficiency couldn't compete with emerging LEDs. Similar trials in Kansas and Durham, UK, also ended with municipalities opting for LED retrofits instead. By the early 2010s, the lighting industry had reached a consensus. LEDs were the future, and LEP would remain a specialized, limited-use technology. Yet it's fascinating to imagine an alternate reality where LEP had emerged a decade earlier before LEDs became dominant. Without the pressure of competing against such a versatile and affordable technology, LEP might have flourished as the gold standard for high-end lighting. Today, the few remaining LEP applications serve as a reminder of what could have been a brilliant but ultimately sidelined innovation.
Some enthusiasts and engineers still hold out hope for a resurgence, perhaps through miniaturization or cost-reducing breakthroughs. Advances in materials science or wireless power transmission could one day address LEP's biggest limitations, reviving interest in plasma lighting.
Until then, it remains a captivating footnote in lighting history, a dazzling technology that arrived just a little too late. So the next time you switch on an LED, take a moment to wonder, what if plasma had won the light wars? Would our cities glow with the crisp, sun-like radiance of LEP, or was LED's convenience always destined to prevail? The story of LEP isn't just about lighting, it's a lesson in how timing, cost, and simplicity can make or break even the most brilliant inventions. The story of light emitting plasma, LEP, is more than just a tale of an obscure lighting technology. It is a reflection of how innovation, timing, and market forces shape the adoption of even the most groundbreaking inventions. As we conclude this exploration, it is worth reflecting on why LEP, despite its brilliance, never achieved mainstream success and what its legacy means for future technologies. One of the most striking lessons from LEP's history is that technological superiority alone is not enough to guarantee commercial success. While LEP offered unparalleled brightness, color accuracy, and energy efficiency, it was ultimately overshadowed by LEDs due to cost, convenience, and timing. This phenomenon is not unique to lighting. History is filled with examples of superior technologies losing out to more practical or cheaper alternatives.
The Betamax versus VHS battle in the 1980s is a classic case where superior video quality lost to affordability and longer recording times. Similarly, the electric car was technically viable in the early 20th century but was sidelined by gasoline engines until modern environmental concerns revived interest.
LEP's fate mirrors these stories, reminding us that market adoption depends on a delicate balance of innovation, accessibility, and timing. Another key takeaway is the importance of infrastructure and scalability in determining a technology's success. LEDs thrived because they could be easily integrated into existing lighting systems, from household bulbs to streetlights, without requiring specialized components. LEP, on the other hand, demanded custom-built microwave drivers and ballasts, making retrofitting difficult and expensive. This infrastructure barrier limited its applications to niche markets where its advantages justified the extra cost and complexity. Had LEP arrived at a time when industries were more willing to overhaul lighting systems, perhaps before LEDs became entrenched, its trajectory might have been different.
The rapid advancement of LED technology also played a decisive role in LEP's downfall. In the early 2000s, LEDs were still expensive and relatively dim, making LEP a compelling alternative for high-performance lighting. However, within just a few years, LED efficiency and affordability improved exponentially, erasing LEP's competitive edge.
This highlights how disruptive technologies can emerge and dominate at astonishing speeds, leaving even the most advanced alternatives struggling to catch up. The lighting industries.
Shift towards smart and connected systems further cemented LED dominance, as their digital nature made them ideal for automation and IoT integration. LEP, with its analog microwave-driven mechanism, was inherently less adaptable to these emerging trends.
Yet despite its commercial struggles, LEP's legacy endures in the lessons it offers engineers, entrepreneurs, and policymakers. For engineers, LEP serves as a reminder that even the most elegant technical solutions must consider real-world constraints like cost, manufacturability, and user convenience. For entrepreneurs, it underscores the importance of timing and market readiness. Launching too early or too late can be just as damaging as having an inferior product. For policymakers, LEP's brief use in municipal lighting trials demonstrates the value of testing emerging technologies before committing to large-scale adoption. Beyond these lessons, LEP's story also invites us to imagine alternative technological futures. What if research had focused earlier on miniaturizing LEP components or reducing production costs? Could partnerships with major lighting manufacturers have accelerated its development and adoption? Would a stronger emphasis on its environmental benefits, such as reduced material waste compared to filament-based bulbs, have made it more appealing in an increasingly eco-conscious world? These hypothetical questions are not just academic. They can inform how we approach future innovations in energy, transportation, and other critical fields.
Today, LEP technology still exists in specialized applications where its unique properties justify the expense. High-end film production, scientific research, and horticultural lighting continue to benefit from its unmatched light quality.
Some researchers even speculate about reviving LEP for next-generation applications, such as advanced medical imaging or space-based lighting systems. While a full-scale comeback seems unlikely, LEP's underlying principles, plasma excitation, electrode-free design, and full-spectrum emission could inspire future breakthroughs. As we look toward the future of lighting, emerging technologies like OLEDs, laser diodes, and even quantum dots are vying to surpass LEDs. Each of these faces its own challenges, much like LEP did, but they also carry the potential to redefine how we illuminate our world. The story of LEP teaches us that progress is rarely linear. Sometimes the best technology doesn't win, but its ideas live on to influence what comes next. In the end, LEP remains a fascinating what-if in the history of lighting, a brilliant innovation that under slightly different circumstances might have changed everything. Its legacy is not one of failure but of resilience, reminding us that even technologies that fade from prominence can leave an indelible mark on the path of progress. As we turn off the lights on this exploration, we are left with a final thought. The next revolutionary technology may already exist, waiting for its moment in the spotlight. Will it shine brightly like LEDs, or will it flicker briefly like LEP, only to be remembered as a dazzling near miss? Only time and the complex interplay of innovation, economics, and human choice will tell.